Use of machine learning to speed up model-based production strategy optimization. Hello everyone, my name is Miranda. I currently PhD candidate at Universidade Estadual de Campinas, working on the use of machine learning to speed up model-based production strategy optimization, supervised by Guilherme Avance and Dennis Kioser. Production strategy optimization is a challenging task in the field development and management, involving numerous decisions characterized by high investment and multiple variables. These conditions can make reservoir simulation studies time-consuming, leading to a high number of required simulations, as illustrated in the Figure 1. We can observe a typical optimization graph showing the evolution of objective function. Considering that each simulation takes 30 minutes, a process requiring 900 simulations will take approximately 8 days to complete if run sequentially. Optimization algorithms are widely used to reduce computational effort, but complex scenarios may still demand a significant number of simulations. In this way, faster objective function (FOF) based on artificial intelligence offer potential solutions to speed up the process. The Figure 2 illustrates the process FOF. The FOF provides faster estimations of reservoir simulated outputs based on given inputs and consists of different model types, for example a neural network, that replace the most time-consuming parts of the optimization process. The FOF outputs always be returned to validate in the commercial numerical simulator. Faster decision making is essential in field development and management. However, as reservoir models become more complex, traditional simulation methods require significantly more computational time. The Figure 3 illustrates how runtime saves to increase as model complexity grows process. To address this challenge, we evaluate the efficiency and the effectiveness of applying FOF, leveraging artificial intelligence techniques to reliable, accelerate production strategy optimization, reduce computational effort, while maintains accuracy. The methodology of this study is divided into two parts. In the first, we optimize a production strategy using reservoir simulation models and establish a case for future comparisons. We start by selecting a base case and define its parameterization. After we select the optimization algorithm and then proceed with production optimization, generating a quality map to help reduce the search space and define the candidate value positions. Next, we apply a hierarchical optimization process divided in 3 parts highlighted in black, which we define the number and position of values. After we fine-tune value position and completion, and finally we optimize the well opening schedule. In the second part of methodology, we test, evaluate, and apply the most suitable machine learning technique based on FOF approach to speed up the process defined in the part 1 of methodology. Following the steps on the flowcharts, we start with data collection to test, train, and validate different FOF models, and then we select the most suitable. After we define the optimization algorithm, with it we generate new samples and estimate the objective function with FOF, select samples for validation in the numerical simulator, and update the database to retrain the FOF. After, we evaluate the stop criterion and repeat the process until it's satisfied. And finally, we apply the loop to cover each part of hierarchical optimization process. The case study focuses on field C, which is in the early phase of development and present reservoir uncertainties, is a fracture simulation models with longitudinal faults and dual media characteristics. There are 5 trill valves, 4 of which are producers and 1 is injector. It's a black oil model with approximately 126,000 active cells using water injector as recovery method. Including the 5 trill valves, Melo in 2021 developed an initial strategy using reservoir engineering knowledge, which were added 4 producers and 2 injectors, totaling 11 valves, highlighted with the red colors in the figure 6. Now I will present the results to optimization using reservoir simulation models. In the figure 7, we have a typical optimization graph showing the evolution of the objective function over the hierarchical phases, highlighting the best strategy achieved in each phase. First, we optimize the valve number and position, shown in blue, comparing it with the initial strategy. In this phase, 677 simulations were run, resulting in a gain of 12.3%. Next, in the fine-tuning phase highlighted in orange, we compare it with the previous phase. 914 simulations were run, achieving a 2% improvement in the objective function. And finally, for the valve position well opening schedule, shown in green, 256 simulations were run, achieving a 2.7% of gain. For fourth application, we have a similar graph. In the optimization of valve number and position, shown in blue, fourth achieved the same result. Were necessary run 286 simulations, improve the objective function in 12.3%. Next, in fine-tuning, highlighted in orange, 368 simulation was run, resulting in a gain of 1.2%. And finally, for the valve opening schedule, shown in green, 204 simulations were run, achieve a gain of 2.7%. In the figure 9, we compare the value obtained with reservoir simulation models and FOF, highlighting the response quality in green. Note that the FOF error stays within the margin of error for an optimization process. In the figure 10, we compare the number of simulations used in each part of the hierarchical optimization process, highlighted in green the speed up of each process. In the first hierarchical phase, there was a 58% of speed up, followed by 60% in the next phase and 20% in the final stage, resulting in an overall speed up of 54% with a quality loss of less than 1%. These are our key outcomes. The fourth, accelerate process without compromising the result quality, and reduction of computational dependency, enhanced options for fast evaluation. However, as the hierarchical optimization process becomes more refined and variability decreases, the benefit of both becomes less significant due to the large complexity in the final stages. I'd like to thank you all for your attention and for listening to this presentation. I'd also like to thank the sponsor for their support and Energy Simulation for this great opportunity.